Hello. We'll see when YouTube and Twitch. But YouTube and Twitch are happy right now. Look at that. Okay, let's see what the latency looks like. Someday it'd be nice to get a better streaming setup. No one's there. Like we got 6 people on YouTube. Hello. Say hello. Let's see who's in chat. Okay. So today we're going to be looking at PCIe. A rather, I would like, capable interface that we see on servers, consumer, desktops, laptops. Laptops, you don't really get much access, but I mean, like M.2, Thunderbolt, Oculink. There's ways you can access PCIe on laptops. So here today we're going to look at what I would say is probably the most affordable and small PCIe development platform. A lot of times you don't get a lot of access to PCIe. Your processor, your kernel is managing it. You don't get to choose how your system reacts to it. So, like, if you really want to play around with custom PCIe systems, you're going to probably need at least one FPGA, and a PCIe FPGA is not cheap. The Squirrel or the Nitefury or Light Fury is probably some of the most affordable PCIe devices on Amazon that you can order today and get delivered now. $100 to $150. But we're going to connect this to the Avnet ZUBoard. So the ZUBoard has a Zynq UltraScale Plus, and we're looking at the processor side. So we connected the processor on the Zynq to an Artix 7 FPGA. And we'll look through the block diagrams of those two designs in a bit. Talk about how they work. But we're using the hardened PCIe core in the processor and the softish core. Well, it's like IO is hardened, but we get to play how we deal with TLP packets. And if you don't know what TLP packets are how PCI Express or PCIe talk to each other. And in the end, down at the simple packet level, it's just basic data packets to each other. And what happens at the configuration level, which is kind of micromanaged for us here and in most systems, the root complex assigns an address to an endpoint, and that is basically the mapping our address. So as long as your data packet is going to the correct address, it will go to that endpoint. And there's some memory inside and basically you can write and read to any memory location from any PCIe device. So I'm still trying to figure out why this is not a security issue. If you had a malicious PCIe device, it could read everything very easily. So trust your PCIe devices. But you can create a packet, TLP packet, in your endpoint and be able to read anything. And that's what we're going to try to do today. We're going to try to do software-defined TLP packets using a microblaze and having our root complex be a Zynq UltraScale Plus. If you have any questions, any shout-outs, feel free to talk to chat. I'll try to keep up with it. See if I can. Can I pop out the chat? I feel like there was a way to pop out the chat. Okay, I'll try to keep it over here and make sure if anyone chats, I'll say hi. Okay. Yeah, so PCIe at the SerDes level is differential, but you're not going to see it as that part of the physical layer is all handled for you in these systems. One day it'd be cool to write a PCIe device from scratch with the red clock and the raw SerDes lanes, and to explore how you do it at that level. We won't be looking at that part today. We're going to be mostly looking at the TLP packet protocol level. So for the Petalinux, or no, for the Zynq UltraScale Plus, we're running bare metal today, but we will have a Petalinux demo in the future. So today is going to be purely bare metal, so we can have some very fine control to it. So Linux isn't crashing, there aren't kernel panics and whatnot. We can screw up in bare metal, and it's not a big issue. But we're going to be looking at doing Petalinux level interactions in later videos. Okay, so let's see what's the best. So for now, let's go look at we're going to go look at the block diagram of the ZUBoard. Okay, so for the block diagram, we're going to focus on the processor configuration. This is relatively basic for setting up a PCIe system, but I just want to walk through it. So hopefully I can get this onto a GitHub project in the future. But if anyone wants to see how you manually set up the PCIe, we'll walk through that step real quick. Okay. For some reason, my GUI is screwed up. Need to figure that out. Okay, when you do PCIe, you want to switch to advanced mode. IO configuration. We're gonna go to high speed. We're gonna go PCIe, and we're gonna have well, okay, so it might be best to go here first, where you change to root ports, link speed, and your payload size. So you do 256. Okay, I have to see why I couldn't get that working. Then we go to IO configuration. We have the root complex reset, and then lane selection, and then we go to the block configuration. Okay, so PCIe, we have 2 lanes. We're using the processor system, relatively easy to set up. And then the clock configuration, we're going to reference 100 megahertz. Hey, John. We're going to reference 100 megahertz. And then for the output clock, there's a PCIe kind of like operational clock. I think this is for the PCIe AXI bus. And it's requesting 250. And this is all manual PLL options with this board. So you just need to set that up to 2 and with the IO PLL, and you can have the correct frequency that you want. But that's kind of all you need to set up PCIe. We're not doing anything special. We have the vendor. These are some basic parameters. So this bar is located within the Zynq as like a endpoint for the root complex. I'll see if we can figure out some more information about this later, but there is a 1 megabit bar inside the system. Yeah, I need to read more about that bar interface. Okay, I'll make a note for that. Write a note. Okay, to writing a note myself. Okay. So that's our basic configuration. These are just some LEDs. Right here, we're gonna be using this traffic generator to do PCIe traffic later in our demonstration. Um, it's set up to do write only, and it's doing write only to the address of the PCIe endpoint. And I'll show more of this later, but it's really interesting. Okay, so now let's look at this is our root complex. Now let's look at the endpoint. Okay, so our endpoint is a software-defined TLP packet reader and generator. Let's go to interfaces, interface view. So what's happening here is we have the basic block, and this is doing AXI stream input and output, and these are just very basic TLP packets. We're not doing anything fancy with them, or the system is. And we're basically going to pass that through a data FIFO, a width converter. This is going from 127 down to 32. And then we're putting that into the AXI stream. So the microblaze has AXI stream ports, and you can actually rapidly read and write AXI stream data from the microblaze. And we're going to have the AXI stream output back to a data converter, back to the PCIe Express. And then we have our PCIe pins. This is going to be really cool because we'll be able to look at the low level TLP packets and be able to respond to them via software rather than having this like hardened core, which is in most systems. It's not going to be terribly responsive, but if we keep the packets small and plenty of space between, we should be able to play around with PCIe and manipulate how the TLP packets interface with the root complex. So to keep track of this, we're going to have these two 128-bit AXI stream ports hooked up to a system ILA, and over JTAG we can potentially look at the raw PCIe communication. Okay, so that's our system. Now let's look at it. So this is going to be our root complex, and our root complex is going to have an init function, and then it's going to enumerate the bus. And the enumerate the bus, it's going to look at every potential endpoint and calculate appropriate address space. And you can see down here where we have the 1 meg for the first address bus is at this address. So this is the address space for the root complex, which is interesting. I gotta figure out why the root complex has a bar space. Does anybody know why a root complex would have a bar space? I'm gonna figure that out. And then here is our Artix device based upon the vendor device ID, and this is the address it gives for interacting with the Artix FPGA. So let's set up a few screens so we can watch all this. I wish I streamed 4K to Twitch so people can see things better, but we're going to try looking at this. Okay, we're going to trigger. Okay, cool. Let's set this up. Okay. How are we this? Can that helps? Okay. We're gonna need another one of these windows. Look at the microblaze in action. Let's bring this up so we can look at the full dialog. And then we're going to look at TLP packets and how TLP packets work. Here we go. Okay, I guess that one works. Okay, here we go for this guy. We're probably gonna want to keep this. Get rid of those ones. Okay, so let's do the configuration for this is set up correctly. Okay, target setup. Okay, we're on the Artix for this one. Go ahead and run it. Okay, so now we're going to go to the microblaze. It wants us to send a TLP packet. So we're going to send a very, very basic TLP packet. So we're going to use xyl out 8 to send a byte. So this is, we're going to send 1 byte to endpoint. Save it, build it, and run it. Okay, we sent 1 packet, 1 TLP packet. So here is what our TLP packet looks like. And you're going to be, you're going to want to, let's take this packet apart and look at the different components of it. But first let's show you what we captured. We captured the single connection, and here's the TLP packet. Can I split this? I think I can split it. Can I do, let's see if we go, be able to look at this right away. Say right there, let me do new group. That's not what I wanted. Can I get this to be a new virtual bus? Okay, this is the word 0. Okay, let's go 30 up to 61. Virtual bus, the word. Did not like me. And the word 1. And then we're going to go to 62 to 5, new virtual bus. That we did not do correctly. $64. 95. We want 4 is 1. That's correct. Then we want the E. So the E is going to be 95 down to 64. Virtual bus. D word 2. Let's do 96 to the top. Virtual bus. D word 3. Okay. And then if we zoom in, we can see it. So let's reorder these. Okay, now we see the header, the length, I think. Well, that's no, that's like the first byte that starts. And then the address and the data. Okay, we have it working. Now let's go look at what these TLP packets are. PCIe Express is not a bus. We're sending packets in kind of like a localized network. So here is our D words 0, 1, 2, and 3 of a 32-bit addressing. If you want to go to 64-bit addressing, there's additional information that happens. Not the best format, but here we go. So packet transmitted, we're going to have a write packet, so we're going to start with 4. Our length is how many D words of data we have. We're going to have 1 D word of data. The next one is how many bytes we're using. We're sending 1 byte. So this is a 1 for us and an F for them because they're sending 4 bytes. Won't stay 1, 2, 3. You asked about bandwidth or throughput. Sorry, let me talk back. Okay, so back to the question. Okay, music lyrics. I've been out. Yeah, okay. Mindshare books on PCIe. I'll take a look at those. And then John. So you're saying the root port bar allows for address translation. A bar is enabled. Any packet received from the PCIe link that hits a bar is translated according to the PCIe AXI translation rules. Yeah, I'm gonna have to look at the technical reference manual. I want to get some more details on that. The Monse asked about AXI limiting the throughput of PCIe. We're doing AXI stream and not AXI 4. And AXI stream is just a data stream. There's no like handshaking, no protocol. AXI stream is just a constant stream of data. And you can manipulate how wide it is so you can get as much data as possible. So since we're doing AXI stream, there shouldn't be any limits to the throughput of the system. Sorry, I should have a mental reminder to check chat more often. Okay. Then we have our address and our data. Okay. So let's play around with increasing our data packets. Okay. So if we go back here, let's now try X16. We'll do 2 of them. We're going to build it and send it over the system. Okay. So now, once again, we have a write 1 D word. We're going to be doing 2 bytes. So that's your mask right there. We're going to be looking at 2 bytes, and the address has changed a little bit. We have different offsets here, and then we have our data, and we have to assume everything after the data is garbage because these are all Fs, and that's a 100. So those are 2 byte packets. And now if we can look at the at our ILA, we can see that we were able to do that within like 6 cycles. This doesn't really happen if you're doing this on a Linux system. When you have to have several layers of kernel calls or something like that to do these PCIe transactions, you're not going to get this level of back-to-back transactions with a Linux system. So it's kind of cool. In bare metal, we actually have pretty optimal PCIe connections. So bare metal PCIe is effective at transferring data. But let's try to transfer more than just 2 bytes at a time. We should be able to transmit up to 128 bits or 4 bytes per clock cycle. Or not 4 bytes, 16 bytes per clock cycle. Let's see how much better we can get. Okay, so let's look at, your traditional 32. Okay, once again, write packet, 1D word. Our mask is all 4 bytes, and then we have our data word at the address. So this all makes sense. This is our simple 32-bit transactions. But let's up it a little bit. So we're about to do a 64-bit transaction, and this is going to take 2 D words to transmit. We're going to build it, and we're going to send. Okay, so now we have something completely new. We have our write packet, but we have 2 D words this time. Our mask is twice as wide, and we have our first 32 bits and our second 32 bits. So this is how we're going to transmit 64 bits per PCIe transaction. But you can see we still have a bunch of wasted space in our TLP packet. So let's try to push this to the limit. And though our system supports 256 bytes per transactions, my DMA transaction only does 128 bytes. But let's go ahead and see what happens here. Also, here's our 2 bytes of data at a time. Okay, so we're gonna try to use some ZDMA. So ZDMA, XZDMA is our DMA buffers built into the system. There's actually 7 of them. We're just going to use 1. Actually, there's 16? There's 16 of them, I think. 8 of them or whatever. I have 8 listed here. But you can interlace them to basically do constant data transmission. And that's kind of like how a really good scatter-gather driver will come into play to really get data between your root complex and your endpoint. But we're just going to do a single instance of the DMA transaction. Go see how it works. Okay. We look at all the data we sent. Now we head up here. This is where we want to be. We're sending repeating 0123 0123 0123 in this transaction. So now we're going to send 20 D words, right? So that's going to be 20 times 32. Actually, it's going to be 32 times 32. So right, 32 times 32. Right. So D word is 32 bits, and we have 20 hex. It's 32, and now we're going to times it by 32. Oh, so are we sending 1,024? Are we sending 1,024 bytes? We're only supposed to be able to do 256, right? Okay. Okay. So 20 times 30, that's 32 times 32. Okay, yeah, maybe we're sending 1,024 bits per packet. Ah, look at that. We can, yeah. Well, let's see. Let's go look at our bus. Did we not trigger? Weird. It should have triggered. definitely triggered here. Okay. It just says an OR gate. Let's try doing this again. I want to see. Thanks, John. It would be great to see the Petalinux package up and running. Why are we not seeing the T-valid? Okay, we did the ZDMA. We should be triggering off of the Rx side. So let's go ahead and drop you. And you should be valid. Let's go ahead and rerun you, I guess. Oh, this is screwing us up. There we go. Microblaze. Okay. Now we're gonna run. Yeah. So the issue was the 64-bit was triggering too early, and I didn't get the window for the larger transaction. So you're right, music lyrics. So it just needs a little slight modification. So now, if we go back to the ILA window and we zoom in. Oh, I forgot to rebuild it. Okay, rebuild. Go ahead, trigger, run, and then launch. I want to see our transaction. Okay, so we are sending 16 bytes. So that's gonna be 1 byte or 4. Okay, so 16. 3. Oh, yeah. We gotta do by bytes. There we go. So we're doing 128 bytes. We're doing 1K bit, but 128 bytes. I don't know how to push up to 256 bytes is what I was wondering. Okay, so there we go. A single ZDMA transaction over the PCIe system of 128 bytes. Currently we're only doing one, or no, we're doing two, and we can see that the ZDMA has a pretty big overhead. It spends more time down than it does writing, and that's just the way the ZDMA works. What you do is you interleave it with your other ZDMAs, and you can get it to go much faster. Another thing we can do is we can do a traffic generator. So back in our block diagram here, Flow Navigator, IP integrator, we have a traffic control generator. And if we jump to the correct address, we can just make the data flow. So let's see if we can do this the correct way. Okay. So if we do register read, right? There is, okay, targets. Do I need a target? Let's see, if we do target 7, we have, oh no, read. Targets. Targets. It doesn't look like it's aware of it. Target 13. RRD. Yeah. RRD sys. Okay, it doesn't know. But if we do a memory write to 04002, right? Yeah, oh no, A 0020061. Let's get the microblaze up here so you can watch it go crazy. We're now sending constant traffic data over PCIe. And if we get the pause, we could see what the packets look like. But let's go ahead and look at it in the block diagram. So we're now doing a traffic generator producing data over the system. We're going to turn off the auto trigger. Calm down. Okay. So we zoom out. They're just sending constant data. Where's the packet? It's supposed to be divided into packets, I'm pretty sure. Oh, did we probably overflowed the microblaze. Okay, so let's turn it off. We broke the microblaze probably. And just look at it beginning. Okay, so the microblaze is broken. So we're going to reprogram it and turn it on and turn it off. Okay. Back at the microblaze. Oh, you still had data that was buffering. Okay, let's reprogram this again. Clear out all that data. The microblaze clearly can't keep up with the traffic generator, which is interesting. Okay, so we're going to turn this on, and then we're going to turn it off. We've already sent enough data. Now I want to see what the packet looks like. Oh, I forgot the trigger. Okay, let's let it finish and try again. Okay, we're going to do microblaze, trigger ILA. Okay. So let's do this, run this, trigger, do that. Okay. Clear out this guy. And then we'll do the Zynq device next. Program this, clear out its history. Yeah, Mona say 1, 2, 3. That's a great thing I wanted to try. So the R5 processor has access to the PCIe device, right? So theoretically, we could pass something down to the R5, and the R5 could use low-level access, DMA, real memory, physical memory addresses to probably speed up your PCIe communication. So it might be advantageous to have the real-time R5 processor manage your localized hardware accelerator. I think that's a really good point. Rather than having Petalinux try to handle it with a bunch of the kernel, if you're, if it's a trusted hardware accelerator, it's a one-to-one connection, you could drop down it to the R5, and the R5 could do low-level commands while Petalinux runs on the A53s. Okay, so before we turn this on, we're going to figure this. I want to see what this does. Okay. So this is what the traffic controller looks like. So it's doing 128 as well. Maybe there should be a way to do 256. I'm surprised it's not doing 256. We'd pick 256 in the block diagram. Data width is 128. That's the bit width though, right? Yeah, so that's bit width. That's not. First length I did 256, so that should be doing 256. So somewhere it's being scaled down. Maybe I'm not configuring it correctly for 128. Maybe somewhere in the root complex we can make sure. Okay, let's go here. I want to see if there's like a 256 thing here. 56. Be in the H right here. 256. Nope. Is there a burst size? Hardware H, next best location. There has to be something that figures the 256. Ah, well, we're not going to find it here. Okay, so I'm not sure why we're not doing 256. We're doing 128, which is great. Been having a fun time trying to get that to work. Okay, so now let's look at a write request and try to get the microblaze to respond appropriately. So here you want to do read request. Okay, so what we're gonna do is go back to hello world, and we're gonna do a xyl in instead of a xyl out, and we're going to play around looking the microblaze to respond to the bare metal system. So what we're gonna say here, let's go 10. We're gonna do xyl in. We're gonna build it. Let's clear out this history real quick. Okay, now go. We're gonna send a TLP packet, and let's see what it looks like. The processor is gonna get angry because it's gonna basically stall. We're gonna stall the processor on a read. Okay. So we have a different packet today. So we don't have the read request, we have a write request. So let's go look at the read request. So we're gonna have a length of 1D word and a tag and a flag. So we want to make sure, I think we have to have the tag on the way back, right? I don't know what the completer ID is. The completer ID. Well, let's try this basic thing. So that's going to be 2, 3. So it's going to be an A. So it's going to be a 4A1. Okay. So we need to do it. What's the other one we want? We want to do a put. So we're going to do a put 0x4 a 0, 0, 0, 0, 0, 1, right? Oh, on the 0, 1. Okay. The tag in this situation is a 1. Is that right? Tag. Okay. Yeah, so tag is going to be a 1, and lower address. Wow, we have a subscriber. Thanks for subscribing. Ugh, always got to me. Okay, so thank you, Lucas. Feel free to say, um, to add any commentary to the chat. Okay, so we want to send 4. Byte count is 4. Byte count is 4. It's weird. There we go. D word to byte count. But I'll take it. And this needs to, we'll do a 0, 1 there. And the tag. So we're gonna do requester was 0, right? We didn't have any ID here. Requester ID is 0. Okay. Then we're gonna tag is going to be 1. So it's just okay. So basically lower 2 bytes. It's this address. Okay, so it wants okay. So the lower address does not match. This picture is wrong. Okay, so we want to pick the lower address bits, which in this situation 10. So we want and there and there. Okay, I think so. Yeah, he didn't. And then the data. Okay, the data. Dead. Yeah, then I think we need to do a T last. How do we do T last? I think it's here. Okay, they don't do a good enough job. I think it's going to be this. Okay, I need the microblaze guide. Microblaze. Okay. 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 What? Okay. Yeah, so it looks like we just need to do a C put at the end for control. And that should tie it low. Okay. Let's see what happens. Build that. Now we want to look at the read response. Be interesting. Also, oh no, let's get rid of that. I don't need any that works fast enough. Writing. Okay. On the hardware. Make sure we are properly triggering on the manager. So the microblaze interface is a direct axis stream, right? So these commands allow us to read and write, not that one, this one. So those microblaze commands allow us to read and write to this. So we're controlling the endpoint in this situation mostly. 1, 2, 3. The microblaze is reading the raw TLP packets for the endpoint, and we are going to write. We're going to attempt to write the raw TLP packets back. Go ahead and grab the other T-valid as well. Down on 1. Have OR gate. Go. The happens to our system here. Okay. Rerun this. Okay. Let's see. Did it even trigger? Had that. Okay, that didn't trigger at all. Did that not work? Yeah. What? Let's go ahead and grab this here. Rebuild this, and let's only look at up arm. Okay. Place code. Okay. Did we trigger? Yeah, we are active. What did we send? Okay. Be last. Dead beef. Okay. Let's see if it works. Seems okay. Let's try this again, but I want to put let's put this trigger at 1000. Okay. I want to see how far away it is. Okay. So, it's taking a long time to respond. Interesting. It might be too long for the processor. That's a long time. But let's see if it works. Going back to here. And we're gonna say That's 0. That's here. Let's test. That's where we're going to do that real quick. Build, run, make sure we see it, then try to. Okay, so we go here. /r/. Show was okay. Missing any comments? Nothing so far. Okay, the read was 0. Let's try this. See if it changed. Wasn't happy about it. Okay. These should be relatively quick instructions. Okay, we want to get rid of that. No string. These should all be super low level. Okay. So the issue, I think, is when we did the string, you don't want to do strings. They're going to slow down your real-time processing. So let's go ahead and just see what we do without. This should be fairly quick, like on the order of like 10 instructions. Oh, look at that. Perfect. Big X. And what is the distance? Okay, that's much better. Look at that. It was 100 cycles. 180 cycles it took to respond. Really? I guess there's the FIFO, the packet size conversion and whatnot. Taking 100 cycles to respond seems kind of crazy. Okay, yeah, let's run it. Did we run it? Did I? Yes. Yeah, let's rerun it, I guess. Oh, it didn't like our data conversions. Okay, we can fix this. We can fix it. That's nasty. But I'll take it. Anything? Let us let us ignore this. Well, let's put this after this. Is there anything? Okay, for this one, let's just do the Xyl print F and say read R. Let's just say R backslash R backslash N backslash R. And we're going to that. Those ones don't really matter. But let's see. Okay, this should be super basic. And let's optimize. Optimize properties. The build variables. Debuild. Where's the flags? Tool chain editor. I think settings. Settings. Right here. Optimizations. Most fly. Flying close. Okay, sorry to make this as fast as possible. Okay, build. And run. So the Xyl in, okay, won't say 1, 2, 3. Yes, the put FSL is the microblaze writing directly to the AXI stream. The Zynq Xyl in is basically an AXI memory command. And here, the Zynq as the root complex is reading a specific address that's associated with the PCIe. So it goes from the processor to the AXI interconnect to the PCIe a bridge to the Artix FPGA to the microblaze and then all the way back. So there's a lot of little steps we're going through. Okay. I want to see how fast this one's going to be. Trigger that. Okay. Run. We go. Dead beef. Perfect. Okay. Here. How fast was it? Ah, we got much faster. Beautiful. Beautiful. Ah, 30 cycles. We got to 30 cycles. Ooh. Okay. How do we make a software? Okay. The next goal for me is I want to make a software defined PCIe endpoint that you can easily change the behavior of the response. But will the microblaze be fast enough? Oh. Maybe we have a microblaze splitter. We split it up between different systems. Because our bandwidth is not being able to parse everything every cycle. We want to speed up the microblazes. We want to maybe have a microblaze between for each different interface, and then have a logging system that just kind of captures the data statistically on the other side. Okay, I like this idea. Okay, so that was kind of the goal of my stream today, was to do a Microblaze software defined TLP packet. We can send a TLP packet of a read request. We could try to do something silly. We could try to send a write request to the processor. So let's try that. Let's try to do what XDMA does real quick. This would be really funny. Okay, so if we go back to what the write request is. Okay, yeah, go back here. Zoom in. So we want to do a 1, 1OF, and then we just want to do zeros. Okay. Where do we want to do this? I guess we could do it right here. We're gonna take 3 of these. We're gonna do 0, 0. So we want the tag, do tag of 1, and yeah, we'll keep our that's going to be our request ID, and the address we're going to do 0, and this is going to use C. Okay, now what we're going to do is we're going to trigger this again. We're going to trigger this on 16, and we're going to see if the processor responds. Okay, I didn't like that. So maybe we need to put a filler. Should be seeing something. Why is it not going through? Okay, let's try doing this one again. Okay, go to the trigger. Okay, let's try putting this here. So we'll send our message, and then we'll send a read request. Okay. Okay, and if we run this, now Did we try this again? Maybe I'm just not building it. Okay, we built it this time. Hopefully it works. Yeah, Mosa, you're right. I'm so used to it auto building sometimes. Okay. Now we go back here. This again. One more time. You can do it. I believe in you. Okay. Cool. So here we send the right response. Does the system come back to us? Didn't respond. Maybe it was, let's try doing this. SB, run it. Okay, we're ready. Oh, we created a cycle. No, we did it. We were successful. And now it's alive and it's not gonna stop. Okay. Um, this is my fault. This is my fault. Okay. Stop the processor. Stop it. Stop it. Where's the processor? Stop. Targets. Stop. Oh, we break something. Marketplace. Okay. So this works, but let's try it without repeating it forever. Okay. Hopefully it's running. Oh, we didn't build. We didn't build. We didn't build. It's gonna be okay. Okay. Okay, it responded. And then we did a response. Okay. What data did it send? It said the data, a read response, 4 bytes, and 00, and it says it's 4E020014. Okay, here comes the most important thing. We go here, we go targets, right here, we do memory read 00. Or 2E24. Yes, it read the data correctly. Okay. Our request, I want 20. Give me 20. Boom. That's it. We're gonna request it. We're gonna finish it. Oh no, we have to read it. 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 Right. I get so. Okay, yeah, let's see right there for now. Okay, so this is how XDMA, this is how DMA in PCIe works. We have an engine inside the endpoint that sends a packet to the system. Requested 20. What did I get? Yeah. Where's my response? Oh, I turned it off. Okay. So we did request 20. And it only gave us one. Weird. Right? What am I looking at? I'm saying here. No, this is the length of our message. How do we... Okay, how do we resolve this? I think we need to look at Xyle in. Okay, how about you? Write request. Let me write. Do you have anything useful on length? Okay, so let's try to do a write request for 64. So the way we're going to figure this out is we was 64 here, and we're going to add this tvalid here, and or it's up. Trigger run. I want to see what their message looks like. Did I build this? I might have not built this. Oh, it restarted the processor. Okay. I'm going to build this one. Load it. Go here. Read it. Still waiting for a trigger. Okay. Run. Okay. Trigger. does it look like? Okay, let's try 2FF. So we're gonna try 2FF. See if this gets us 2. Okay. Oh, it worked. Okay. Time to be greedy. I want 20. Give me all your data. Give me all the data from your processor. Oh, look at that. Okay. So you're saying if we go here, do a memory, no, down here, do a memory read of 0, 0, and we want to do 32 of them. Okay, it's all zeros. Where's an interesting place to read? Okay. So we're gonna try to read 40. 40 should be the theoretical max. So did we run this? It doesn't look like I liked it. Or did it not? Okay, Monose. Is the microblade set up to deem these put commands to the XP, or is it busy handling transitions of each put command? So these are assembly instructions that should just be placing these directly down. Oh, it did 2 transactions. Look at that. I requested 40, and it did it as 2 separate transactions. Crazy. Does that mean you'll give me more? Will you give me more? I asked for a ridiculous amount of data. Will you give me that data? You will. You'll give me the data. Oh, crazy. Okay. Okay. What happens if I interleave these? Um, let's let's do something. Let's just do something crazy. Um, okay. So what we're gonna do is we're gonna do 4 of these, 3 of these, and we're gonna switch these to 2, 2, or 3, and 3. What will you do here? Will you try interleaving them? Will you assign them to different DMA engines? Nah, it doesn't look like it. The most proficient system. Okay. Well, the interesting thing here is that even when we have the PCIe running at full bandwidth, right? Like, we still have a ton of downtime. Hmm. Okay. But we can request as much data as how big is the length? Oh no, we can only request 10 bits. So we can do 0, 0, 2, 3. Okay, so the max should be, that should be our theoretical max in this address bus. Okay, let's run it, see what happens. What happens when you request all the data? Okay, so if we put this into a Thunderbolt system, and then we have, you plug into a USB, you can just copy someone's entire DDR space immediately. All their memory map stuff. Oh, the CPU. True. It'd be interesting to try this. We could try this on a real system, or we should try this on the Petalinux system. Let's try it on the Petalinux system. I'm curious. Okay, we're gonna reboot this and try on the Petalinux system real quick. This is gonna be fun. Okay. Boot pins. Booting up into pink. Pull up a terra term real quick and see what we get going. We're gonna have to reboot anyway, so it's not gonna be a big deal. All right, I'll show you in a second. Oh no, did the weird thing again. Reset port. That way I want. Ow. How do you do this sometimes? Drop you back down to 9600. Drop you back up. Whatever. I don't need you to be working. I'm gonna program the device with the same interface. Reboot it. Enable it. Then go crazy. Okay. Let's do this. Go ahead, work on that. We're gonna have to do a reboot. Might have to SSH into this sucker. Oh, you want me to do a sudo reboot, don't you? What's my password? You don't know. Oh, look at that. It works. Okay. Try opening up that terra term clean one now. Okay, setup, serial port. 100. Okay. There we go. Okay. I really want to see if we can copy the base address with the system enabled. But you have a good point. We could go try this on a real, more heavy-duty system and see how the processor, how we profile the PCIe transactions when we request a large amount of data. We're gonna sudo su. Okay. PCIe-BBV. Actually have a lot of information. Disabled. Okay, we have to go enable that. So let's go sys. No, bus. No, sys. Yeah, bus. PCI devices 1. This is where we want to be. Yeah. We're gonna echo 1 to enable to lspci-g are now enabled. We don't really care about the address. We're just gonna read 0. I went to this one went to E, and the bar space here did not assign any bar space. It doesn't look like they're assigning bar space for the bridge, memory behind bridge. Okay. Why give this guy same address? I don't know. Okay, so let's try to run the processor. So we're gonna go here. We're gonna do a modus. And we're gonna run. How does the Petalinux? Look at that. They did a great job. Okay, now let's try to request more from the Petalinux. Petalinux. I mean, Ubuntu. Pink. Petalinux. Monstrosity. Give me more data. Do you use more DMA engines? Are you better handled? No, it's still just doing 20s. It's still just doing 20s. Okay. So yeah, it seems like a limitation of the processor, not the OS. So it could be a clock speed. I mean, I'm only running 1 lane right now. We could run more lanes. We could run more systems, but this is what it's set up. Well, in all honesty, the system's set up for 4 lanes, and I'm running it at 1 lane. That might be the issue. I'm only running 1 out of 4 lanes. Let's say that's the main issue here. I'm only running 1 out of 4 lanes, and that's the limitation for all of this. Okay. Yeah. So I'm gonna say this is a lane issue, potential processor issue, but whatever. Thank you for joining us, Manose, John, Music Lyrics, anyone else in the chat. We were able to do some fun PCIe debug. Any final comments? Any suggestions for next time? Yeah, no problem. Okay, final comments from me. Let's expect this to be on. Hopefully I can get this on GitHub by the end of May. So if anyone wants to follow along, they can follow along. And the goal is to create a microblaze software-defined system that you can do TLP manipulations of an OS. And we'll be able to a malicious endpoint, not malicious, a debugging endpoint where you could plug it into your computer, you could plug it into your laptop, and you could just DMA everything out of your system. There's no if you saw, there's no handshaking, there's no security. The Petalinux OS just gave me raw data because I asked for it. I find that so weird funny. Oh, okay. Good night, everyone. See you maybe tomorrow, maybe Monday. We'll see.